Okay, let's go ahead and get started. So today I want to complete our discussion of the Lorentz transformation. So I remind you that the basic idea is that if you have two observers, say an observer S, who is measuring spatial and time separations between events, say delta x and delta t, and an observer S prime who measures separations between events delta x prime and delta t prime, and observer S prime is moving with velocity v in the plus x direction with respect to observer S, then that means that the spatial and time separations are related by the Lorentz transformation formula, which I've already written a million times, and I'm going to write it down a million times more, because it is really the basic formula from which all good things stem in special relativity. And it's something that you should know both in its quantitative content and its qualitative effects as well as possible. So today, I would like to complete our discussion of the basic implications of the Lorentz transformation formula for various effects in special relativity before moving on to discuss exactly what this implies to us about the geometric structure of space-time. Question?
Yeah, you let the
primes. Thank you. Good. Primes. Lots of primes everywhere. Good. Any other questions? Thank you. Good. Okay. So we saw that the form of the Lorentz transformation allows us to understand exactly how time dilation, the relativity of simultaneity, and length contraction come about. We also saw that it allows us to derive one other additional interesting effect, that of velocity addition. And the first thing that I would like to do today is describe to you one further effect that can be understood using the Lorentz transformation rules, namely that of the relativistic Doppler effect. Relativistic Doppler effect and the relativistic Doppler effect is among the most interesting in special relativity because it is actually one of the easiest to observe. And indeed, it is observed all the time in astrophysics and cosmology. And indeed, the relativistic Doppler effect is the primary tool that we have in order to understand the structure of our universe at its largest scales. And as we'll see later on in this course, when we briefly discuss cosmology, it is this effect which really allowed us to first understand that the universe was expanding, which, of course, was a fundamental change in our picture about the dynamics of the evolution of the universe as a whole. Okay. So what is the relativistic Doppler effect? Well, let's consider the following scenario. So let's consider a source which emits light with frequency nu. So if you want a model for what it means to say that a source emits light with frequency nu, you could also think of this as a source which emits a signal, let's say a burst of light, for example, once per time interval (1 over nu). So if you want to think about what it means for a source to emit light with a given frequency, you could think about that source as somebody standing there turning their flashlight on and off and emitting a burst of light from that flashlight once per a given time interval, and that time interval is the inverse of the frequency. Indeed, that's something like a bit of a mechanistic model for what light is. So if you think of light as a wave, you could think of these bursts of light each as the peak of the wave. Or if you think of light as a particle, you could think of these bursts of light as individual photons. As we'll learn in the quantum mechanics portion of this course, these are indeed both incorrect in details, but correct in some qualitative features, ways of understanding the properties of light. So let me now remind you of the ordinary Doppler effect. So the ordinary Doppler effect is the following. So let's imagine that we have this source, okay, there it is, and it's emitting light. So there's the light it's emitting. Here's me, drawn with the usual artistic skill. And let's say that this source is moving with some velocity v towards me. Okay. So if the source is moving towards me, then the usual Doppler effect says that the frequency increases. Whereas if the source is moving away from me, then the frequency will decrease. And there's nothing fancy about this. This is just a property of wave mechanics, if you want to use fancy language, or a property just of geometry and clocks and stuff like that, if you want to use a more prosaic language. This is why, for example, the sound of a car honking at you will increase in frequency as that car rushes towards you. And then after it runs over you, it will decrease in frequency as you lay there on the ground having been smashed by the car. Now, of course, if we want to consider light, then we'll need to consider special relativity. Okay? And so in order to do so, let's use our Lorentz transformation rules. Okay? So let's say that I am in frame S, and the rest frame of the source, namely the coordinate system in which the source is not moving, I will call S prime. And let's go ahead and compute the time interval at which I will receive bursts of light from the source in terms of the frequency of the source nu in the frame at which it is at rest. So the burst interval, the time it takes between the emission of bursts, is I'll call that delta t prime in the frame where the source is at rest. And that will be 1 over the frequency which I'll call nu prime, in the frame where the source is at rest. So in the frame of the source. And the time between the emission of pulses then will be, as observed by me, will be related to this time delta t prime by the usual time dilation factor. So in my frame, S. Okay. But we're interested in understanding the time interval between the receipt of bursts from the signal, from my point of view, not the time interval between the emission of bursts from the signal. So we need to take into account the fact that both the light and the source are moving in order to calculate the time difference between the receipt of bursts of light from my point of view. Okay? Is that clear? Any questions? No questions. Good. Okay. So the first thing to note is that in between two emissions of bursts of light by the source, the burst has traveled a distance c delta t in my frame, because the bursts are light and they travel at the speed of light in every frame, which is c gamma delta t prime. And it's traveled this distance when the next one is emitted. And it's emitted from a different position as the original burst was emitted. And it's emitted from a position which is closer to me by a factor v delta t, the velocity of the source from my frame, times the time interval between the emission of the burst, or v times gamma delta t prime. So that means that if you think of these bursts traveling towards me, the distance separating them is just the difference between it's just the difference between this and this. So it's going to be c minus v gamma delta t prime, or c minus v times gamma divided by nu prime, the frequency of the source in its rest frame. So the time interval between the receipt of bursts of light is simply that factor divided by c. So it's 1 minus v over c times gamma times 1 over nu prime. Or let's write that out a little bit more explicitly. That's 1 minus v over c divided by the square root of 1 minus v squared over c squared times 1 over nu prime. And 1 minus v squared over c squared has another name. That's 1 minus v over c times 1 plus v over c. So we could rewrite this as the square root of 1 minus v over c divided by 1 plus v over c times 1 over nu prime. So the frequency that I observe is just the inverse of that. So I'll call it nu observed, and it's 1 plus v over c divided by 1 minus v over c times the frequency emitted by the source. And this is the formula for the relativistic Doppler effect. Sorry, I try and write my nus as being very curly so you can see the difference between them and v's. Hopefully, this is a clear way of writing the formula. Any questions? Okay, let's take a minute and think about the implications of this formula. So, if v is positive, that implies that the nu observed is greater than nu emitted. So, in other words, light which is emitted from a source traveling towards us is going to appear bluer than it would if the source were sitting still. So we often say that it is blue shifted. And likewise, if v is less than 0, that implies that light is red shifted. Indeed, Edwin Hubble's very famous observations about a century ago involved studying in detail the spectrum of light that was emitted from distant galaxies And he observed that the light from distant galaxies was redder than the light from nearby galaxies. And that if one used this formula, the relationship between the apparent velocity of the galaxy and their distance from us was linear. And so, based on this, he concluded that more distant galaxies were receding away from us with a velocity that was proportional to their distance. And this is known as Hubble's law, and it is one of the core principles, if not the core principle of cosmology. And it is the basis for our modern understanding of the expansion and evolution of the universe. Yes?
Is it the same if you're moving toward an object that is moving like?
Absolutely. Absolutely. Excellent question.
So
Yes.
does that mean that if a traveler goes at the speed near the speed of light, all the photons that are received will be generated?
Absolutely. Absolutely. If I if I move at a constant velocity towards a source, then by the principle of relativity, that is the same as the source moving with constant velocity towards me. And so the light that you see will be highly blue shifted. Absolutely. That's why in Star Trek, when they're going very, very fast, no, that's not quite true. Actually. It's just because they're moving quickly. But yes, good point. Good. And there are two interesting cases of this formula that I think are worth pointing out. Okay. So the first is that as V approaches C, namely if you have an object that is moving towards you at a velocity that is approaching the speed of light, then the observed frequency goes to infinity. Whereas as V goes to minus C, meaning that you have a source which is moving away from you at a velocity approaching the speed of light, then the frequency observed goes to 0. So if nu observed is going to infinity, that means you have infinitely highly blue shifted gamma rays which carry, as V approaches C, an infinite amount of energy. Okay, that sounds very bad. That sounds very dangerous. Whereas if an object is going away from you at the speed of light, approaching the speed of light, then the photons emitted by that object are infinitely redshifted. They carry 0 energy, and effectively that object is going to become unobservable because the energy carried by its photons as it moves away from you at velocities approaching the speed of light will get lower and lower and lower. And as we will see, this property here is characteristic of something known as an event horizon. And I think we'll have at least a brief discussion of general relativity and black holes in this course when we discuss that in more detail. So here I have considered so far motion in parallel to the direction of the radiation. Or in other words, I have considered sources which are moving either directly towards me or directly away from me. So we can also consider motion perpendicular to us. So, for example, this is me. If we have a source which is emitting radiation, which I'm going to observe, but which is moving at some velocity v, say in the y direction rather than in the z direction, then one would also be interested in understanding the relativistic Doppler effect. And in fact, I'm not going to derive the answer for you. You're going to derive the answer for you in the next problem set, which I hand out. So I will just tell you the answer, which is that for photons which are emitted when the object appears perpendicular to us, namely when the object is at its point of closest approach if it's moving on this line of constant velocity. Or then nu observed is related to nu emitted by this relativistic factor, just the gamma factor. And that's easy to understand. It's because this source, if you're the source and you're turning your flashlight on and off once per second, but you're moving relative to me with some very large velocity, 1 second to you could be a very long time for me. And so I will perceive that these bursts of light are emitted at time intervals much greater than 1 second. And there's a little bit of a caveat here, which is that when we talk about direction perpendicular to us, there are really two things that I could be talking about. So let's say that here is our source, moving at constant velocity on this line, and this is me standing right here. Then we could either talk about the point when you actually are at the point of position of closest approach, or you could talk about the point when you appear to be at closest approach, because you're moving with some velocity v, and it takes some amount of time for the light to get from you to me. So those are actually two slightly different times, and you'll get two slightly different answers, as you will see in the problem set that I will hand out on Wednesday. And in general, for motion which is neither parallel to nor completely perpendicular to the line between us and the source, there will be a more complicated redshift factor, which is the name that we sometimes give to the coefficient sitting in the Doppler formula, which is neither. So it's easy enough to guess that factor. So we guess that factor should just be gamma when the motion is perpendicular to us, and it should be gamma times 1 minus v over c when the motion is parallel to the direction of the source. So it's not hard to guess that the correct formula is something like 1 minus cosine theta v over c, where theta here is the angle of motion. So relative, I suppose, to the tangent, namely to this vector that I have drawn up here. So that when theta is equal to, I guess it would be the angle relative to the line between us and the source. The derivation is very similar to the derivation that I just gave you, so I'm not going to go through the details. If you really want to see the derivation of this formula, then I suggest you consult your textbooks. I think it's worked out in both of them, actually. Okay, so this concludes my discussion of what I consider the basic effects of special relativity, including the more interesting features of velocity addition and the Doppler effect. What I'm now going to do, probably for the remainder of this week, is a discussion of some of the more general implications of special relativity, which before diving on next week to a discussion of relativistic dynamics, of energy and momentum and forces in special relativity. But before I move on, let me just pause and see if there are any questions. Yes?
For that diagram there, the point where it appears to be perpendicular, wouldn't that not be after when it's actually perpendicular? The time?
Let's put it this way. What do I mean? Okay. Yes, I guess you're right. I sort of misdrew this, maybe. The point when it appears to be perpendicular, when it's actually perpendicular is this one, and the point when it appears to be perpendicular would be this one. Yes, you're right. I actually drew that incorrectly. You'll have to draw it correctly for your problem set, but I have a PhD, so I don't have to draw it correctly. Yes?
If you think about, could you still use that to say, when you see it there,
Absolutely.
it's in fact
Absolutely. in order to understand the difference between the two, you just need to calculate that angle. Okay. So there's some relative angle that I call theta here. Absolutely. Okay. Good questions. Other questions? Good. SpaceTime. So, what I would now like to do is to think a little bit more deeply about the nature of some of the effects which we have considered. And I would like to use these effects in order to understand a bit more of what is called the geometry of spacetime and the implications that special relativity has for the ways that we think about space, time, and the relationship between them. So, let me start by reminding you of something that we already know. So, given two events, we have seen that the spatial separation, say delta x, and the time separation, delta t, between those two events are observer dependent. In other words, they depend on the coordinate system in which they are measured. So sometimes we will restate that a little more succinctly by saying that delta x and delta t in and of themselves have no physical meaning. That's not really a great way of phrasing it, because of course delta x and delta t do contain interesting physical information about the relationship between those two events. But they also contain other information which is not physical. Information about the observer who is measuring delta x and delta t. For example, I could have two events, and I could be in a frame where they are simultaneous, so that delta t is equal to 0 and delta x is not 0. But you could be in a different frame where the events are not simultaneous, so that delta t is not 0. That tells us that in and of themselves, in and of itself, the quantity delta t has no physical meaning. Whether it's 0, positive, or negative is simply dependent on who is making that observation. And in order to understand exactly what this observation means, I would like to remind you that this is something that you have already seen, essentially, in a very different context. This is similar to a situation that you know from geometry. So instead of considering two events that take place at a position and a time, consider 2 points in the plane. And let's say that I have 1 point here and 1 point there. And if I wanted to, I could describe the positions of these points with respect to some coordinate axes, x and y. And I could measure, for example, delta x, the x separation between those points, and I could measure delta y, the y separation between those 2 points. But as you know, the values of delta x and delta y depend on the choice of coordinate system. For example, I could choose some new coordinate system. So instead of measuring things in terms of the x and y coordinates, I could define some new coordinate axes. Let's call them x prime and y prime. And I could try measuring the x and y separations, delta x prime and delta y prime, in this new coordinate system. And of course, the values of delta x prime and delta y prime will not be equal to the values of delta x and delta y, but instead they would be related in some way. And so if I denote by theta the relative angle between these two coordinate systems, they'll be related by a formula that's something like x is cosine theta x prime plus sine theta y prime, and y is minus sine theta x prime plus cosine theta y prime. Delta x prime and delta y prime, the differences between the coordinate values in the two different coordinate systems, of course, differ from delta x and delta y. Or, to put it another way, delta x and delta y themselves have no geometric meaning. The numerical values of delta x and delta y will depend on the coordinate system that you use to label these 2 points. By the way, is this expression x is cosine theta x prime plus sine theta y prime familiar to you? Raise your hand if it's familiar. Good. So what is the quantity which has geometric meaning? Well, the quantity that has geometric meaning is the distance between the 2 points. And how is that determined? So the length L, defined by the equation L squared, is delta x squared plus delta y squared, i.e. determined by the Pythagorean theorem, does have geometric meaning. What does it mean that it has geometric meaning? It means it is independent of the choice of coordinate system. So, for example, if you computed the separations delta x and delta y between these points in one coordinate system and compared it to that in another coordinate system, you would find that delta x, delta y themselves would change, but the length delta x squared plus delta y squared would not change. Or, to put it a different way, if you were just to compute, say, the distance between a point in the origin and the xy coordinates, and compare it to a point in the origin and the x prime and y prime coordinates, using this formula up above, you could easily check that x squared plus y squared is equal to x prime squared plus y prime squared. Okay. Now, the formulas that I have written down are hopefully quite reminiscent of the formulas that we have seen for the Lorentz transformations, which, as with this simple case of a rotation of the coordinate axes, relate the two different coordinates that one uses to describe events at different positions and times in different coordinate systems. So the question that we then want to ask is there a combination of delta x and delta t in special relativity which is invariant under the choice of observer, i.e. under Lorentz transformation? And this would be the quantity that would play the same role in the theory of Lorentz transformations that the length between two points would play in the theory of Euclidean geometry. Question?
At the bottom of the previous page, when you said that the x and the y tensors have geometric meanings?
Have no. God. Thank you. Have no geometric meaning. Yeah, I leave out words. It's something that happens. Thank you. Other questions? Okay. If you played around with it long enough, you would figure out the answer. The question I have posed is not a particularly difficult one. So let me just tell you what the answer is, and then we can check that it is indeed the case. Given two events with spatial separations delta x and time separations delta t, let me consider the following quantity. It is the difference between the square of the x separation, their spatial separation, and c squared times the square of their time separations. So here I have used the notation delta x and delta t to refer to these separations in one coordinate system. And in a second coordinate system, S prime, we could go ahead and compute this guy. So it would be delta S prime squared, which is delta x prime squared minus c squared times delta t prime squared. So let's just go ahead and compute that. What's delta x prime? Well, we could just go ahead and use the inverse Lorentz transformation rule. So delta x prime is gamma times delta x minus v delta t. So that will be gamma from delta x prime squared, it'll be gamma squared times delta x minus v delta t squared. And then you'll have from delta t prime squared, so delta t prime is gamma times delta t minus v over c squared delta x. So pulling out that factor of gamma squared, we'll get c squared times delta t minus v over c squared delta x squared. So I've just used here the inverse Lorentz transformation. So let's go ahead and compute that. Well, we have gamma squared. So let's first compute the coefficient of delta x squared. From this first term, we get a 1. And from the second term, we get minus v squared over c squared. Okay. From the square of this term, because you have a minus c squared out front. And then you have the square of minus v over c squared, so that's plus v squared over c to the fourth. Put it all together, and you get minus v squared over c squared. Now let's go ahead and look at the coefficient of delta t squared. So I'll pull a c squared out front, so that from this term here, you get a minus 1. And from this term here, you get plus v squared over c squared times delta t squared. So I pull the minus sign out front there. So this is 1 minus v squared over c squared times delta t squared. And then let's look at the delta t, delta x cross term. So from this first formula, what do you get? You get a minus twice v times delta x delta t. And from the second term, you get plus twice v times delta x delta t. So they cancel. And if we remember the definition of gamma as 1 over the square root of 1 minus v squared over c squared, then gamma squared cancels the coefficients of delta x squared and delta t squared. So we see that this is delta x squared minus c squared delta t squared, or it's just delta s squared. So although delta x and delta t themselves depend on the coordinate system in which they are defined, the quantity delta s, which is known as the invariant interval, delta s, defined by the equation delta s squared is delta x squared minus c squared delta t squared, is between two events is independent of the choice of observer doing the measuring. So any observer could measure the spatial and the time separations between those two events. Delta x and delta t themselves will depend on the choice of observer, but the combination delta s will not. And the name invariant interval should be somewhat clear. Invariant comes because it is invariant under a Lorentz transformation. And interval comes because it's like a distance, but it's also not like a distance in ways that we will now discover. So it's an interval, it's not a distance. Before I proceed to discuss the physical interpretation of the invariant interval, let me see if there are any questions.
You said it's not a distance, but it's just not an interval.
Yes, it's sort of a distance. It's an invariant interval. In some cases, it's a distance. In some cases, it is not. Questions? Okay. By the way, those of you who have seen special relativity before, have you seen the invariant interval? Okay, so this is new. Good. It always feels nice to be doing something you haven't seen before. So what is the interpretation of delta x? Well, the first thing that I want to point out to you is that although I've written the formula delta s squared is the difference between two squares. So delta s squared can be either real or positive or negative. So that delta s can be real or imaginary. So let's first understand these different cases where delta s is real or imaginary. So, and in particular, delta s will be real or imaginary depending on whether delta x squared is bigger than c squared delta t squared or less than c squared delta t squared. So in order to consider the difference between these two cases, let's first consider the simplest case when delta s is equal to 0. Okay. What does it mean for delta s to be equal to 0? It means that delta x squared is c squared delta t squared, or delta x is either plus c delta t or minus c delta t. So we have a name for pairs of events that are related by delta x is plus or minus c delta t. It means that the two events can be connected by a light ray. Because light rays travel at velocity c, for which delta x is c delta t or minus c delta t, depending on whether the light ray is traveling to the left or to the right. And in that case, we give a name to these two events. We say that the events are null separated. Or sometimes we say that they are light-like separated. Okay. So that was the easiest case. Let's now consider the case where delta S squared is negative, i.e., delta S is imaginary. So my claim is that this implies that there is a frame in which the events are simultaneous. Meaning that they... Oh, I'm sorry. I got that wrong. That's the case where it's positive. There's a frame in which the events are spatially separated. But take place at different times. God, I can't say anything right. I just restated the same wrong thing. God damn it. Okay. There's a frame in which the events, I haven't had enough coffee today, in which the events take place at the same location. But different times. Sorry about that. Meaning that there is a coordinate system let's call it S prime, such that delta x prime is equal to 0, but delta t prime is non-zero. So let's quickly see why that is the case. So given an original frame where delta x and delta t are non-zero, then delta x prime is gamma times delta x minus v delta t. And that can be set to 0 if we choose the frame which is moving at velocity v with respect to our original frame S, where v is just given by solving that equation, so it's going to be delta x divided by delta t. And delta S squared is delta x squared minus c squared delta t squared. Being less than 0 implies, just by dividing both sides of this equation by delta t squared, that delta x over delta t squared minus c squared is less than 0, or the velocity squared is less than c squared, so that the absolute value of the velocity is less than c. So in particular, that means that we can choose an observer moving with a speed less than the speed of light, to whom it would appear that the two events take place at the same location. And in this frame, delta x prime is equal to 0, and so delta s squared is just minus c squared times delta t prime squared. So we usually give a special name to this quantity when delta s squared is less than 0. So delta t prime is then the time between events in the frame where they take place at the same location, namely where they are not moving, i.e. their rest frame, and we usually give a name to that. So I'll be calling it delta tau in this class, just to distinguish it from delta t prime, which because it has a t and a prime, you might think is coordinate dependent. But remember, this is the time between the events in the frame where they're not moving. So that's a coordinate independent statement because it's the time between the events in a particular frame. Or it's related to delta s squared by this formula. And it is called the proper time between the events. And we don't ever even need to actually go ahead and find that coordinate system where the two events are at rest, because you could always start in any old coordinate system and compute the invariant interval between those two events. And if it's negative, you could just take the square root of minus delta s squared over c squared in order to find the proper time between the two events. The time between the two events in the frame where they are at rest. Let me pause here and see if there are any questions. Next class, we'll find out what will happen if delta s squared is positive. And we'll continue our discussion of the physical meaning of space and time in special relativity.